So I'll be talking about mechanochemical activation of basaltic fines. My PhD student, Sofian, is leading a lot of this work. The other authors are listed here as well. So I really should change these slides because I'm preaching to the choir here. So I won't spend too much time on them. Long story short, concrete is great, but concrete is also kind of bad because it contributes 6 to 8% to all global CO2 emissions. And you'll read articles saying, oh, the most destructive material on the planet. Well, you know, we should actually take a look at some of the numbers that are associated with emissions on a mass basis. And if you look at those numbers, you can actually see that compared to almost any other material, the emissions of cement and concrete are really quite low. Although it has to be acknowledged that cement, which is only 15% of the concrete by mass, is responsible for a significant proportion, 80 to 90% of concrete emissions. So it's pretty straightforward that we must reduce cement emissions. And these days, everyone has a roadmap, and these roadmaps ask us to reduce our emissions by 20, 30, 40, 100% in the next X, Y, Z years. So where does the CO2 emissions in cement arise from? So the process of making cement vastly simplified is there. You heat up limestone, clay, and a whole bunch of other materials to about 1500 Celsius to produce OPC. The vast majority of emissions come from two things, which is the decomposition of limestone, the heating, and particle size reduction operations. So 60% is roughly from the limestone decomposition, which is not a reaction you can avoid if you use limestone. So a lot of people, as an example, brimstone, are looking into can we actually replace limestone with something else. Generally speaking, if you reduce cement content in concrete or the limestone content in cement or in clinker, you will reduce emissions. To me, one of the best technologies in the last few years in the US is Portland limestone cement, which, you know, with this one little trick, you can save 10% carbon emissions, that sort of thing. Several folks will disagree with me, several folks will argue with me that it's actually very complicated, that Portland limestone cements are responsible for all the evil in the world, but I think it's a pretty cool technology. A lot of the other newer techniques, technologies, etc., have not seen much testing at the concrete scale. Thankfully, though, the DOE has decided to seriously believe and invest in concrete and decarbonization of other materials. So this is coming, it's just a matter of time. Now, very quickly, supplementary cementitious materials. So these are finely ground amorphous calcium aluminosilicates. They are fantastic. Everyone loves them because you can replace a substantial portion of the cement and concrete using SCMs. And, you know, on top of that, they actually help with strength and durability as well. It's not that every supplementary cementitious material helps every property of concrete, but generally speaking, use supplementary cementitious materials, they will make your concrete better. Most commonly, fly ash, slag, silica fume had and continue to be used. These are industrial byproducts, but because of changing industrialization trends, we have increasing shortfalls in these materials. So now there's the question of how do we identify novel SCMs? You've heard about calcined clays. That's a fantastic technology, something that many are working on. Harvested fly ashes are something else. Natural pozzolans, I think, have a lot of promise as well. But at the same time, a lot of people are looking into manufactured SCMs, Terra CO2 as an example, that thermal activation, mechanochemical activation, or CO2 mineralization can be used to potentially transform or improve inert feedstock into reactive materials. So my focus is going to be on mechanochemical activation, and largely I'll talk about basaltic fines and their mechanochemical activation. So essentially, mechanochemical activation is high energy grinding. We do it in a planetary ball mill. In the previous session, a ball mill was shown. A planetary ball mill is slightly different. It has, you know, this dual rotation. The RPMs is a lot higher as well. 400 RPM or something like that is the maximum. In our machine, others go a little bit higher. Broadly speaking, we've worked on basaltic fines, mine tailings, clays, but really, as I said, basaltic fines will be the focus of my talk. One of the most important materials for mechanochemical activation are clays. You heard previously about specific issues of workability, flow retention with calcined clays. And some of the people who have been doing this at scale, carbon upcycling or polysius, have shown that mechanochemically activated clays potentially have the promise to not have this issue with workability, The theory is, it gets into complexity, and I'm not saying that you should mechanochemically activate all clays, but the statement I'll make is that if your clay is less than 30% kaolinitic content, there's probably good amount of potential in mechanochemically activating it, both in terms of reactivity and workability improvement compared to the calcined clays. So obviously clays has been in focus, but others have worked on other materials. I think Professor Swarzan is sitting in the back of the room. He's done a lot of fantastic work on a number of different feedstocks using mechanochemical activation. So others have looked into CO2. That is, when you have high calcium and magnesium products, during the grinding, you add a little bit of moisture and then you hit this with CO2. I think for certain specific products, this makes a lot of sense. I personally would not do it for fly ash or slag, but for steel slags or recycled cement products, this could be a very useful solution. Okay, so some results. We had a basaltic fine that we took. This material was very, very inert. And we said, hey, we are going to mechanochemically activate it. We varied the BPR, which is the ball to powder ratio, so just the amount of charge versus the amount of material. And we also varied the grinding time. So what we see is a very classic mechanochemical response in that the specific surface area increases. It actually increases very, very rapidly. And then it goes down as you continue to grind. So it goes down or it levels off after, in our setup, at least 15 minutes of grinding. So we are attributing this to various sort of agglomeration, aggregation, and similar properties. I will be the first to admit we don't have a full handle on the nature of these agglomerates or aggregates. We will at some point. So anyway, the specific surface area increases from about 2 to between 5 and 12. So it's a very significant increase in surface area. And of course, you increase reactivity by increasing the surface area, maybe. So we see a little bit of a trend that the specific surface area reduces as the BPR increases. If you're interested, preprint is available on ResearchGate and SSRN, I guess, but I'm also happy to send you the paper. Let me know. So particle size distribution. So the initial particle size distribution is very simple. It's near normal. The peak is about 10 microns. Then after mechanochemical activation, this is almost like parting the Red Sea sort of behavior where you get a very complicated particle size distribution, which is bi or trimodal in nature. So the explanation that I have, at least at this point, is that the fines, which are typically less than 1 micron, is of course created by fracture. The particles around 10 microns in size are either unaffected particles or particles created from fracture of yet larger particles. And the particles which are about 100 microns in size, these presumably are some sort of aggregates, agglomerates, etc. So we put these under the electron microscope. Unsurprisingly, the results are rather consistent with the particle size distribution. So the raw basaltic fines, the particles are quite angular in nature. They're about 10 microns in size. After MCA, the particle size distribution is clearly broader. And we do see fines about 10 micron particles and coarser particles. So that's very consistent with the PSD. And we see some sort of aggregate or agglomerative behavior. The other thing we see is, generally speaking, we haven't quantified this yet, but there seems to be a marked change in the morphology. That is, the initial morphology, which is angular, starts to become somewhat spherical. So this is great news for the workability, right? That you are forming spherical or near spherical particles. At some point, we'll put in some time, we'll actually get some parameters and say, the aspect ratio or the sphericity changes. We haven't yet done that. So on the other hand, the XRD results are, to me at least, a little bit easier to interpret. So we haven't done internal standards yet, so we kind of estimated using a few different approaches, degree of amorphization. And essentially what you see very clearly is after mechanochemical activation, the peaks drop. And I realize just the drop in the height of the peak is not necessarily a quantitative indicator, so take it with a grain of salt. But in all cases, as you continue grinding, the peaks drop, drop, drop. However, there is clearly some heterogeneity here, meaning that some peaks vanish very quickly, whereas other peaks persist. And what we found is, qualitatively speaking, the ease of amorphization, that is the ease at which these peaks vanish, depends very strongly on the hardness of these particles. So again, this is just an estimate, but in this system we find that as the most hardness goes from 2 to 7, the ease of amorphization, the persistence of those peaks changes markedly. So again, these are just estimates. I realize that these are not the most perfect numbers, but that's okay for now. So if you look at the degree of amorphization again, and you plot it against the grinding time, there seems to be a pretty bilinear response, limited number of data points, but it kind of seems that this goes up and then it kind of levels off, although it's not exactly, it is not exactly horizontal. It does go up a decent bit. So we said, okay, all of this is great, but I mean, are these actually useful materials? Are we, making them actually reactive? And the good news is we absolutely are making them reactive. So we did a modified version of the R3 test, pretty similar to the R3 test. It's not going to make a big difference in this context, but we see very clearly that as the BPR increases and the grinding time increases, the reactivity increases. And from these R3 and similar tests, the threshold is about 100 joule per gram of SCM. And you can see that, beyond a certain grinding time or beyond a certain BPR, you pretty easily exceed the level of reactivity needed. So again, with increased grinding time and increased BPR, the reactivity increases. So to me, this is one of the more interesting results. So I said before, right, that the increase in specific surface area clearly results in an increase in reactivity. Actually, that's not the case. We plotted various measures of particle size and of specific surface area against the reactivity, and we did not see any correlation. Yes, we can kind of make the argument that, because of the agglomeration, etc., we probably don't have the best estimates of particle size or specific surface area, and I think that's a reasonable argument. However, here's my thinking. I think the reactivity is driven by the amorphous content, because basically you can take inert powder and you can start to size fractionate it, but unless you start to get to like nano sizes or something, if something is inert, it generally will stay inert regardless of what the specific surface area is within certain limits, okay? In this case, what I think happens is that beyond 15 minutes, the specific surface area is really not changing, right? So that increase in reactivity because of the specific surface area is largely controlled by what happens in the first 15 minutes. So when we plot, on the other hand, the degree of amorphization and the heat release, we actually see a really nice, strong linear correlation that suggests that the heat release basically depends on the degree of amorphization, and you have this nice relationship. We tried to include SSA in this. We tried to plot separately with SSA. Absolutely no relationship was seen. So we conclude from this, at least preliminarily speaking, that over a wide range of amorphous content, the amorphization controls reactivity. What I don't know here is a planetary ball mill is a very specialized piece of equipment. I don't know if you just take a standard ball mill and you just grind for a very long period of time, if you would get similar results. There are a number of other different mills and milling configurations, etc., that we haven't explored, although others have. Okay, one material is fantastic. What about others? We've actually tested a lot of other materials, and so have others. I only show here the results for 12 materials. So MCA generally works with some caveats. Meaning, what we see is that if you plot the increase in reactivity versus the initial reactivity, you see, this kind of exponential relationship. The exact relationship is not so important, but basically what you see is that when you take materials which are very reactive, you don't really do anything to them. So presumably this is because these materials are already highly amorphous to start with. A flash or a slag has an amorphous content somewhere from 60 to 90%. You're not going to make the amorphous content 200%, right? So a slag, actually, we essentially found no real change in reactivity, because presumably what happens is you're not really increasing the specific surface area all that much for these materials, because you are getting the finer fraction, but then you're getting the agglomerates as well. So generally speaking, this works fantastically for filler materials, for materials which have very, very low values of reactivity. But going forward, it's not useful to do this. I would not do this, especially because it's a pretty energy intensive technique, for a fly ash, for example. So yeah, so that's the explanation that I just gave, that the highly amorphous materials have already high initial heat release. There's limited further amorphization, so limited increase in heat release. Okay, can we do anything about cement pastes and mortars? We did limited work here, but essentially what we see again is a clear effect of the amorphization that we generate reactive SCMs. So at 30% replacement, the control is up there. I switched those out. I'm sorry, I don't know why I did that, but anyway. These are switched out, the MCAs are the other way around, but the MCAs show substantially higher heat release than the raw materials, but at the same time lower than that of the control materials. Now, we actually looked at cement mortars as well, and this is a work in progress, but we see, for example, improvement in workability. We don't actually see a huge loss after mechanochemical activation in the slump flow, like one would expect with calcined materials. In the basaltic fines, the workability is only slightly reduced, and this is interesting because the specific surface area has actually increased greatly. So presumably there's a competing effect of the spherical particles being generated, which are kind of compensating. We see in compressive strength that over 7 days, significant improvement beyond the raw supplementary cementitious materials for, not the raw SCMs, the raw inert fillers and the mechanochemically activated materials. Also at 28 days, we see this sharp increase in bulk resistivity with respect to the control and with respect to the unactivated materials, which confirms again that we've generated substantially reactive SCMs. So with that, I'd like to conclude. So we studied MCA in the lab for basaltic fines and other materials. The physical changes are really quite complex. There seems to be, trimodal sort of particle size distribution generated, agglomeration in spherical particles. But for the reactivity, I almost feel like this does not matter all that much. But the amorphization, where the extent depends on phase hardness, this seems to control the reactivity. But the spherical particles generated seem to be improving the workability, a work in progress again. But we have shown MCA for many different materials, and the increase in reactivity depends on the initial reactivity. We see in cement paste and mortars increased heat release, mortar flow, strength, bulk resistivity improvements. With that, I'd like to thank my funders, my research group, and you. Thank you.